So our next talk will be by Yizhou Zhang from Waterloo, who will talk about design, where paradigms meet.
Right, so I'm Yizhou Zhang, and I'm assistant professor at the University of Waterloo. So today I'm going to talk to you about our work on a language design at the intersection between machine-checked proofs and object-oriented design. Okay. So you've probably seen and used machine-checked proofs. So these are sometimes called mechanized proofs. These are formal proofs written in a proof system like Rock, Lin, Agda, Isabel, right? And someone who designs and implements programming languages. We care most about two types of applications. So the first type is to prove meta theories about programming languages we design. So things like type safety, parametricity, non-interference, so on and so forth. And the second type of applications is verified compilers, right? We want to prove that what the compiler outputs actually matches the semantics of the program in the source language. And two prime examples here are COMSERT and KKML. The bottom line is this, that nowadays we pretty much expect that serious claims about correctness come with machine-checked proofs. And with the growing use of machine-checked proofs comes a programming challenge, namely how to modularly extend and compose proofs. And so let's take the simply typed lambda calculus as an example. Okay. So STLC is a standard example in a programming languages theories course and in the PL textbook. And many texts walk through a machine-checked proof of simply typed lambda calculus via the usual progress and preservation lemmas. And after that, they start adding features like recursive functions, product types, sum types, exceptions, you name it. Right? And each extension brings new rules, new cases, and new round of proof editing. The typical pattern here is to first copy the old development and then patch it to handle the new constructs. Right? So this pattern works, but it's fragile, it's repetitive, and it's not modular. So proofs are not reusable, and they don't compose the way we'd like. It may appear striking that we programming language researchers care deeply about modularity, but when it comes to meta theory, when it comes to mechanized meta theory, that modularity is often non-existent. But this is not a new problem. It's actually an old one reappearing in a new setting. So this problem is known as the expression problem. It's a term coined by Phil Wattler in 1998, but even then he called it a new name for an old problem. The question is this. So we want to have a language where we can add new features, where we can add new cases to a data type, and also we can add new functions over those data types without touching or recompiling existing code and still retain static type safety. Okay, so that's the expression problem. Now that same challenge is reappearing in the context of mechanized proofs. So here we want a proof language where we can add new syntax, new rules as new cases to inductive types, and also add new recursive functions, new induction proofs over those inductive types. And we want to do this without touching or recompiling existing proofs. And we want to still retain the logical consistency of the proof language. So this is not just an academic puzzle that we made up to entertain ourselves. It shows up in real systems, actually. So take RISC-V. Right? It has a small clean base ISA, and everything else is just an extension, like vector instructions, floating point instructions, custom crypto instructions. So you can build these features on without touching the base ISA. So the extensibility and the modularity enable customization of features for performance and other design goals. Same with MLIR, right? So it makes it possible to have custom dialects and transformations across multiple levels of abstraction. So this problem, this expression problem, is very real. Extensibility and modularity do matter in practice. Now, back in the setting of mechanized proofs, of machine-checked proofs, the problem shows up not only in meta-theory proofs, but also in compiler proofs, in compiler verification. So here's Magnus Myring raising a key challenge in compiler verification in his keynote at last year's PLDI. So here Magnus pointed out that compiler proofs are often hard-coded to specific languages. They're not reusable. So take a common feature like variant types or pattern matching. Can we isolate just that part of the language? Can we verify the translation of that feature once and reuse that verified component across different compilers that incorporate that language feature? So right now, that kind of modularity is non-existent, and each compiler has to redo the work. But solving that problem would be a big step toward scalable, modular, verified compilers. So that brings us to the key idea driving our work. What if we looked beyond traditional proof languages? What if we borrowed ideas from the object-oriented world, where extensibility and reuse are first-class concerns? So this slide here captures the vision. On one side, we have machine-checked proofs, precise, tightly typed, zero tolerance for non-termination. So the big ideas here are like inductive types, induction principles, dependent type theory, Curie-Howard correspondence, total functional programming, logical consistency. On the other side, we have object-oriented programs. The key ideas here include dynamic dispatch, late binding, inheritance, traits, mixing composition. So these two paradigms represent very different schools of thought. They bring very different assumptions and values. And our goal here is to define languages and proof systems that live in this unified space. And that's where I'm heading in this talk. Language design that we created called Rocket that extends Rock with programming abstractions inspired by object-oriented ideas. And the goal is to combine the mathematical rigor of proof systems with the modularity and extensibility and flexibility of object-oriented design. Okay, so let's ground this in something familiar, the simply typed lambda calculus. So here I'll quickly go over how STLC is typically mechanized in the theorem prover like Rock. So first we define the abstract syntax of terms of programs as an inductive type with 4 constructors: constants, variables, lambda abstractions, and applications. And next is the substitution function, which is recursive on the syntax of terms. And then we define the abstract syntax types and typing rules as 2 inductive types. And we also define a small step reduction semantics as another inductive type. And with these inductive types in place, and with some of these recursive functions in place, we can prove some core meta theories. So first, the weakening lemma and the substitution lemma, and then the big 2, progress and preservation. So all of this is done using structural induction, either on the structure of the abstract syntax or on typing derivations or on stepping derivations. And finally, type safety follows from progress and preservation. So this should feel very familiar to someone who's used Rock or Lang and who studied a textbook like Software Foundations. So now let's look at what happens if we try to extend this developing rock. So one extension here adds recursive functions to STLC. Another extension then adds product types. And each extension brings the same stack of changes, like new abstract syntax, new typing rules, new reduction rules, new cases in some recursive functions, new cases in induction proofs, and fresh round of proof editing. The usual pattern is to copy the old development and then patch it to handle the new constructs. So this already hurts modularity, but it gets worse when we try to compose multiple extensions. We'll have to restitch the base formalization and the extensions together to make the composition happen. So what starts as a clean conceptual separation turns into a tangle of overlapping definitions and copy-pasted proofs. But this creates TDM, obstructs changes, and destroys the clean conceptual separation between extensions. It limits how we scale verified systems. So let's look at how this can be done in Rocket. So we start with the base STLC, the base simply typed lemma calculus, formalized in its own module. This formalization looks much like what we would do in Rock, except that the module here is known as a family. Okay? Here's the key difference. So each extension to STLC is packaged as its own trait. Each trait modularly adds its own syntax, its own typing rules, reduction rules, and adjust those proof cases relevant to that feature we need to add to STLC. Then we compose the base family and the extensions and the traits with this one-liner. Okay. So then the result is automatically a module that automatically gives us a complete machine-checked formalization of STLC extended with the selected language features. So here's what the actual code in Rocket looks like. The base STLC is defining its own family. And now the syntax here is a bit simplified compared to what we have in Rocket right now, but the structure is the same. Okay? The key point is this. Constructors of the inductive types, cases of recursive functions and induction proofs, and even this type safety theorem can all be reused without recompilation. A trait models an extension. The trait is only responsible for adding the new functionality of that extension. Then we compose the base family with the traits into a derived family. And Rocket automatically synthesizes the full type safety proof for the extended language. Okay, so that's Rocket, and hopefully that looks cool. And from this point on, I'll start talking about how Rocket does this. Okay, so there are deep tensions between these two paradigms, between the world of machine-checked proofs and our desire to freely abstract and extend. So we cannot just import an OO abstraction mechanism into a proof language and hope it works. Right? We have to ask ourselves some important questions, like what does inheritance even mean for proof terms? And is late binding compatible with dependent types, with logics? So let's start with the first tension here, closed versus open inductive types. In proof systems, in any proof system, inductive types are close to extension. Once you define inductive type, you cannot go back and add new constructors later. Right? That's by design. It ensures that case analysis is exhaustive. It allows recursive functions to be, so this exhaustivity allows recursive functions and induction proofs to be written by enumerating all the possible cases. And under the hood, the rock prover associates every inductive type with a recursion principle, also known as a recursor. And when we write a recursive function or prove something by induction, we're actually applying this recursor. But here's the problem. All of that, exhaustiveness, recursor, sound induction, sound recursion, they all depend on the inductive types being closed. And if we were to make inductive types open, then those assumptions would break down. To address this problem, we turn to the OO world for inspiration. So in OO languages, there is this idea known as family polymorphism. Okay, so it's a way to define a group or a family of related classes where the meaning of each class, each family member is late-bound. That is, each family member is polymorphic over the current family. This idea comes from OO languages like G-beta, and it generalizes late binding from methods to classes. We take this idea of family polymorphism one step further, and we allow the late binding of inductive types. So for example, consider the term inductive type here. In Rocket, its meaning is polymorphic over the family it's nested within. So if term is mentioned in the STLC family, then it's considered to have 4 constructors. But in the derived family, the term inductive type can have more constructors. And because of this late binding, any code or proof that mentions this term type, like the substitution function, can be inherited and reused automatically because they remain well-typed when reused. Okay? And accordingly, when a trait adds a new constructor to an existing inductive type, it must also handle that constructor in the case analysis, okay, in the recursive function or induction proof. So that gives us open inductive types and still enforces exhaustiveness in a modular way. But late binding brings even more challenges, and one of the most serious challenges is this. Late binding is at odds with definitional unfolding. So let's take the substitution lemma as an example here. So this lemma shows that substitution preserves typing. So it's a standard result in the meta theory of STLC. And the first move in a proof like this is usually to apply the induction principle and unfold the substitution function to look at its definition and do a case analysis. But in Rocket, that substitution function is late bound. Okay? So we cannot unfold because we cannot see the exact definition of the function. Its definition is polymorphic over its enclosing family, so we cannot assume that it is exhaustively generated by those 4 cases. And then we ask this question. Do we really need definitional unfolding, definitional equality to prove the substitution lemma? And the answer is not necessarily. It suffices to know how the substitution function behaves in specific cases. So if we think of the exact definition of a function as its implementation, then these behavioral equalities here are like its specification. They tell us how the function should behave in specific cases, and any concrete implementation of the function can refine that specification by adding additional cases. Okay? So although the new abstraction mechanism hides implementation, we can still use these behavioral equalities as our reasoning principle. So they give us just enough to reason about open inductive types without needing to unfold the definition of recursive functions over those open inductive types. And the Rocket automatically makes these behavioral equalities available in the proof context and has tactic support for them. So that lets us recover the power of definitional unfolding but in a way that's compatible with late binding. Another key tension that we had to resolve here is between logical consistency of a proof language and open recursion. So what's open recursion? Open recursion is at the heart of many extensibility mechanisms, like dynamic dispatch, inheritance, mixing composition, family polymorphism. Okay? So it gives you a way to extend behavior. In practice, open recursion just means parameterizing over self, a self parameter, which acts as an extensibility hook. But there's the catch. Open recursion can create cycles. And cycles mean divergence. And divergence can break logical consistency, which means we can prove contradictions. And when that happens, everything becomes provable and nothing is trustworthy. Okay? So while open recursion gives us the extensibility, it also threatens the foundational guarantees that we rely on. And here's one idea to recover logical consistency. We trust that rock is logically consistent. So if we can have a type-preserving translation from rocket to rock, then we can reduce the question of logical consistency to the rock prover. And here's a first attempt at this type-preserving translation. Here we follow the classic recipe of open recursion. We compile family to a module parameterized over self. And anytime a family member is referenced, we make a late bound. We route that reference through self. So this gives us the extensibility we want. At the end of the day, we will need to take the fixed point of open recursion. But this fixed point here does not type check. Okay? So RAW cannot verify that this recursion is safe. We have to convince to the rock prover that we are not building anything cyclic or non-terminating. To solve this problem, Rocket uses a strategy which we might call well-founded open recursion. So the idea is this. Instead of taking a massive fixed point all at once, we compile family members one at a time. Each member here is only allowed to reference other members in its typing context that are already defined. And we still route the references through a self parameter, but now this self does not stand for the entire family. Instead, it stands for the partial family that has been compiled at that point. So we can break cycles and, by enforcing a well-founded dependency order among family members. And this compilation strategy also gives us something nice, something convenient. So we can recover the iterative, the kind of interactive proving experience. We don't have to define the entire family before we get feedback. Proofs are compiled and checked incrementally as each family member is defined. And the fixed point of this well-founded open recursion can be taken by iteratively instantiating the extensibility hooks. We're using already compiled proofs. So the key benefit of Rocket's compilation strategy here is the reuse of already compiled proofs. For example, when we take the fixed point of that derived family incorporating multiple extensions, we can reuse the already compiled pieces, like the cases of the substitution function here. And each trait contributes its own cases for this function, and those cases are compiled independently. And at fixed point time, Rocket assembles these cases into a complete recursive function using the recursor Rock generates for a closed inductive type. Okay. So the result is, again, a single tree traversal over the abstract syntax. Okay, so now with these tensions resolved, we have a solution to the expression problem for the novel setting of machine-checked proofs. the norm setting of mechanized matter theory. But the expression problem does not stop there. Right? It shows up just as forcefully in compiler verification. So here's how we used Rocket to create an extensible verified compiler framework. We started with a base compiler for a simple imperative language. Then we added a series of modular extensions, each as a separate trait in Rocket. And each of these extensions contributes syntax, semantics, some translation code, and the correctness proof. Now we combine these traits together, and we get a verified compiler for imperative language that supports all of these features. And that's the language on par with what CompCert compiles. Okay, that's CompCert C. So this modular approach lets us select exactly the subset of C features that we need in the compiler, and that's especially useful in a resource-constrained setting like embedded system development, where developers often want to avoid features like dynamic allocation or floating point arithmetic. At the same time, this modular approach also opens the door to future extensions, paves the way to incorporating new features to CompCert C. Now, in addition to this modularity problem in compiler extensions, there is another related problem, another modularity problem in verified compilers. And that problem is concerned with the modularity of intermediate languages and compiler passes. So in CompCert, it's been observed that many of the intermediate languages are minor variations of each other. And the code of those ILs follows a copy and patch pattern. And this isn't unique to CompCert. In KML, the ILs are often defined with excessive boilerplate. It was noted that it would be ideal to define each IL as a readable diff of the previous one in a similar vein to the NanoPass framework form scheme. So TLDR is this. We want the modular ILs and passes to cut redundancy and to boost clarity. So let's see how this can be done using Rocket. So let's say we want to verify a NanoPass compiler containing 4 ILs and 3 NanoPasses. Each IL here is a small variation of the previous one, removing or adding some language feature. We can define these ILs, these intermediate languages, without redundancy using Rocket support for traits. So for example, IL1, the first IL, can be defined by composing a base IL with 3 traits, X, Y, and Z. And the same goes for NanoPasses. Each NanoPass is defined as a Rocket trait, just specifying the program transformation and the correctness proof, the feature it cares about. And here's the icing on the cake. When composed, all of these NanoPasses can be fused into a single tree traversal. Okay. So we keep modularity at the spec and proof level, and also we still generate efficient compiler code. And that's what we call NanoPass fusion. It's modularity at design time and the performance at runtime. And we try to apply similar code organizing techniques to CompCert. So in the front end, we refactored the C to C-Lite pass into a series of NanoPasses. We observed that C-Lite, C# minor, and C minor are very similar, so we refactored them to reduce duplication. In the back end, we refactored an IL called Mac and another called linear to enable more reuse. And for the redundant pipeline, we used Rocket to create an extensible ISA model for RISC-V. And that fits naturally with RISC-V's philosophy, which emphasizes modularity and extensibility at the ISA level. So as a summary, modularity is a cross-cutting concern, in the construction of verified compilers, we needed both across compiler extensions and also in the compiler pipeline, across compiler languages and across compiler passes. So Rocket here doesn't save you from the real work needed for verifying compilers, but it does help you create your own reusable building blocks much more easily. So with that said, I don't want to suggest that we have solved all the problems. There's still much to do. We believe we've only started exploring how far this approach can scale. There are also important questions around usability, performance, and the practice of proof engineering. And I want to mention that my students in Gaga did most of the work here, and I learned a lot from them. Okay, so to end on a more reflective note, I think working on a language design at the intersection of paradigms is fun and deeply satisfying. Okay, so when different schools of thought meet, they bring conflicting assumptions, right? And that clash forces you to confront some foundational trade-offs head-on. It forces you to clarify to clarify what really matters. And reconciling those tensions is intellectually exciting and also highly rewarding. Because paradigm fusion is where new ideas emerge. It's where we get to design new language abstractions and get to mass-based tradition. So in Rocket's case, the challenge is to design abstractions as flexible as OO concepts, but still within the tight constraints of a proof language. That pushes the design space, so new module systems, new extension points, and new ways to think about abstraction and reuse in the context of machine-checked proofs. And what makes it even cooler is when those language abstractions can do real work, make it easier to build extensible, modular, trustworthy systems. And with that, I'll be happy to take questions.
Questions?
In the meantime,
All right, yeah, we can set up. Okay, there is.
So the original CompCert work is not compositional in the sense that the compiler theorem doesn't tell you what happens if you link with code that wasn't produced by the same compiler. Does the case study that you told us about inherit that same limitation?
CompCert is not composition in the sense that
You compile a program with CompCert version 17, and then you compile a library with CompCert version 18 and link them together. There's no guarantee of the behavior.
Right, yeah. So our Rocket port inherits that limitation. Yeah.
Okay, thanks.
If not, let's thank Yizhou again.